Hi guys, so this is Mr. Gron. It turns out we've now got a third cold day in a row, so I figured we should probably do a little bit of real work. So I'm hanging out here with my daughter Estelle. You say hi, Estelle? Maybe not. She's a little camera shy. But this video is going to be kind of a general video, a couple of examples to give you an idea of what we're going to be doing when we get to class on Friday. So just kind of a little preparation video. All right, so for our first example, we'll take a look at what we're going to find out is a relatively simple polynomial. And while it might not look simple to you right now, what we're going to find out is that this is a simple one because we can solve it strictly by graphing. Now, for the purposes of this example, I'm going to do a couple more things to try to make a point and a connection between factors, synthetic division, and the graph of this. So let's take a look at the graph. All right, so taking a look at the graph, I can see why this is solvable just by graphing, because I've got three zeros, three solutions. One of them, the x value is -2, the other one, the x value is -1, and then the last one, the x value is +3. And if the question just asks me to solve where does this equal 0, I could just throw it on my graphing calculator, maybe confirm with the table that the answers are -2, +1, and +3, because if I plug those three x values into this function, the result is going to be 0 for the y value, the output of the function. Now let's say for whatever reason I knew that this was a real 0, that it was a nice 0 because it's -2, but maybe I didn't know that those two were. So let's just take those off and pretend that we didn't know about that. What I would do next would be to remove this 0 using synthetic division. All right, so in order to remove that -2, or more importantly, the factor that comes from the -2, which is x plus 2, we're going to use synthetic division. So we're going to perform this operation. So that'll be -2 being divided into our coefficients 1, -2, -5, +6. And if this is indeed a factor, we should come up with 0 as a remainder in that second box. So the 1 comes down, then -2, because we're multiplying by -2, then -2 minus 2 is -4, -2 times -4 is +8, -5 plus 8 is +3, and -2 times +3 is -6. 6 minus 6 is 0, so that's good. That means that x plus 2 is indeed a factor of this. And what's left over is the depressed polynomial, which would be 1 times x squared minus 4 times x plus 3. And what's important about this part is where those other two zeros are located, where they come from. Now, if the problem was asking us just to factor, what we would have shown here is that our original polynomial, x cubed minus 2x squared minus 5x plus 6, is equal to the factor x plus 2, what we just divided out, times that depressed polynomial, x squared minus 4x plus 3. And if we look back at the graph now, we can see something interesting here that shows that these two things are the equivalents of one another. So looking back at the graph, I now have both versions of the polynomial entered. Only one's showing at the moment. The original polynomial, and then now the one that we took out one factor and rewrote it as a product of two factors. And if we do a little monkeying around with Desmos, we can show that they're the exact same. So if you notice the shape of the graph now, when I switch it to the blue one, the second one, it's the exact same. So what that means is that we took out this piece right here, that x plus 2, which is right here, which has a 0 at -2, and what's left, this part here, is where these other two zeros came from. So if we graphed just this, it would have zeros at these exact same spots. And we can use we could use a quadratic formula, we could just factor this, we could graph just this part to figure out where these two zeros are if we needed to. So let's do that. Let's factor this and see how it looks. So now if we really wanted to factor this all the way, if that was the goal of the problem, we would say that this is equal to x plus 2, and then this second part here is a basic sum and product factoring. We're looking for factors that multiply to positive 3 but add to a negative 4, and that's going to be x minus 1 and x minus 3. And now if we are just looking for it's fully factored. If we're just looking for the solutions where it equals 0, it would be negative 2 for the x plus 2, positive 1 for the x minus 1, and positive 3 for the x minus 3. Now the point of this wasn't to do as much work as possible to prove a point. It's really just to try to show the connection between the solutions of the polynomial, the factors of the polynomial, and the original polynomial form, how they all relate with the graph itself. If this was a problem that came up in the homework, it would be good enough just to graph it and say, on my graph I found negative 2, positive 1, and positive 3 as zeros. But not all of them are you going to be able to do that with. Alright, and then one last thing just to drive the point home a little bit more is looking back at that graph. Now we've got the original polynomial in red and now the fully factored polynomial in blue, and I just wanted again to show that they're the exact same thing. Alright, so let's take a look at one that's just a little bit tougher now. We're not going to be able to completely solve this by graphing. We're going to use graphing to figure out one easy zero that we can remove using synthetic division to start factoring this, and then end up having to use the quadratic formula at the end. Alright, so looking at the graph of this, now you'll be graphing this on your TI-84s. That doesn't work quite as well for making these videos, so looking at this I can see that I again have negative 2 as a solution, so x plus 2 is going to be one of the factors. And my other two are some kind of gross looking decimal numbers. And because we're kind of mean math teachers, we're not going to let you just put, that it's negative 2, negative 1.193, and 4.193. We're going to define these two exactly using irrational numbers, using some square roots in the quadratic formula. So the first step is going to be to remove that x plus 2 that has negative 2 as a solution using synthetic division, and then using the quadratic formula to figure out exactly what these two are in simplest radical form. Alright, so jumping right into the synthetic division this time, negative 2 going into 1, negative 1, negative 11, and negative 10. And that's going to be, the 1 comes down, 1 times negative 2 is negative 2. Negative 1 minus 2 is negative 3. Negative 2 times negative 3 is positive 6. Negative 11 plus 6 is negative 5. Negative 2 times negative 5 is positive 10. And that means we have a remainder of 0. That means that we have, as a factored polynomial, that this is x plus 2 times, and that x plus 2 again is coming from this negative 2.
Look at the plus.
Yeah, I see the plus. That's my son Odin, who's listening in and helping me out with this video now. Estelle went to bed, now he's helping out. So anyway, it's x plus 2 because of the negative 2 that was a solution, and then my depressed polynomial is x squared minus 3x minus 5. So the coefficients from right here are the coefficients, or these numbers, are the coefficients of this part. Now this is not a factorable polynomial, a factorable quadratic, so we're going to have to use the quadratic formula from this point. I know that I have x equals negative 2 from the graph and from the fact that x plus 2 is a factor because this was 0, so that confirms that this is a good solution. Now I need those other two from here. So that is going to be negative b is positive 3 plus or minus the square root of b squared, so negative 3 squared minus 4ac, so 4 times 1 times negative 5, all over 2 times a, which is positive 1. Now, this again is only coming from this part right here, right? The negative 2 we already found by graphing is from this, and then the other two solutions are from this part here. All right, so simplifying, let's see, this is going to be 3 plus or minus. Negative 3 squared is positive 9 minus 4 times 1 times negative 5 becomes plus 29. So if we simplify that, just the discriminant, excuse me, all of this stuff inside the radical equals 29 all over 2. And this actually does not simplify any further. We'll get some where this would simplify, where we'd have to simplify the radical. We'd maybe have to cancel some stuff with the 2 in the denominator. But this is actually as simple as this one gets. So all we have to do now is say that it is x equals negative 2. Throw a little comma next to it. And it is 3 plus or minus the square root of 29 over 2. Now if we look back at the graph, we've got the 1, 0 is at negative 2. If you plugged in 3 minus the square root of 29 divided by 2 into your calculator, you would get this number to the nearest thousandth. And if you did 3 plus the square root of 29 over 2 in your calculator, you would get this number to the nearest thousandth, 4.193. So there you have it. That's really what we're doing in all of 6.5 and 6.6. There's some more details, some smaller topics that we'll wrap up and we'll cover on Friday. But if you can leave Friday being able to do a problem like this, you're in really good shape. We'll also do some with complex numbers where you're not going to be able to actually see the zeros on the graph, and you'll have to use I to define them. But that's the gist of what we're doing, is graphing, finding a zero that is a nice whole number, using synthetic division to remove it from the polynomial, and get it down to a point where we can solve the rest either by factoring or by using the quadratic formula.